API 577 Welding Inspection and Metallurgy. In this lesson, we shall talk about the metallurgy. And in this module, you shall learn about structure of metals and alloys, physical and mechanical properties, preheating and post-weld heat treatment, material test report, MTR, and weldability of metals and high alloys. Welding inspector does not need to have in-depth knowledge of metallurgy, but the basics for the API examination. Structure of metals and alloys. During welding, the metal is melted and mixed or alloyed with flux or electrode coating and then solidified, somewhat similar to a casting process. Metals, when melted, are in liquid state and have no particular structure or orientation. But as the void pool is cooled down and solidified, crystal structures are formed. Physical and mechanical properties of metals depend on the composition as well as the metallic structures. Castings. In order to minimize the amount of machining for complex shapes, castings are used for pump casings, impeller, and valve bodies. It is desirable to keep the size of the grains small because it improves strength and toughness. To do this, the metal can be rapidly cooled, that's called quenching, to prevent formation of coarse structure, and heat input can be restricted. Impurities such as carbon, sulfur, and phosphorus in the metals can change the crystallization of metal during solidification and also precipitate between grain boundaries, reducing strength, ductility, and toughness. To overcome this issue, high purity metals could be used, or oxygen scavengers such as aluminum or silicon can be added during the casting process, which deoxidizes or starves the impurities from reaching the oxygen, and hence the name killed steel, because it's starving these impurities from mixing and starve them from oxygen. For example, prevent formation of carbon dioxide bubbles that embed themselves between metallic grains. This process called scavenging, and steels produced called killed steel or fully killed steel. It also helps achieving smaller grains and minimizing the amount of trace elements that could later on cause hydrogen-induced cracking, HIC, during service. ASME requirements for pressure vessels generally require any steel with a carbon content of more than 0.24% to be killed. Scavenger actually means a rubbish collector in layman's terms. Gases such as hydrogen, if trapped within the metal during solidification, create void and porosity and cause cracking during welding process. That is why moisture and containment need to be removed prior to welding, and low hydrogen electrodes may be used to overcome HIC or hydrogen-induced cracking. Wrought means material that is subject to forming, such as extrusion, rolling, and forging. Forming can be hot or cold. Hot forming, such as rolling, forging, or extruding, is performed above the recrystallization temperature of the material. Grains at recrystallization temperature make the metal behave in plastic manner, allowing them to deform greatly by little application of force compared to when they are formed at cold state. The recrystallization temperature for a steel is typically between 400 and 700 degrees centigrade. Austenitic stainless steel is corrosion resistant because of its chromium content that reacts with oxygen, forming chromium oxide layer protecting the steel from corrosion. When carbon reacts with chromium, forming chromium carbide, it is called sensitization, making the alloy steel vulnerable to corrosion due to depletion of chromium. So sensitized microstructure is the chromium depleted area. Pure iron or ferrite is weak, but with addition of 0.06% carbon, the pearlite phase is formed with improved strength. Welding metallurgy. The welding has three parts: weld metal, HAZ or heat affected zone, and base metal. Weld metal is less homogeneous and less uniform than the base metal, which affects its strength. That is why weld metal strength shall always be equal or greater than the base metal. The solidified weld metal is a mixture of melted base metal and deposited weld filter metal. The heat affected zone is the area next to weld whose width depends on the heat input of the weld. It is the area which is affected, which is heated to 700 degrees centigrade or more, which is the recrystallization temperature of steel. The third part is the base metal beyond the HAZ region. Each type of metal has welding procedural limits within which sound welds with satisfactory properties can be made. If these limits are wide, the metal is said to have good weldability. On the other hand, if the limits or range of welding are narrow, welding parameters, the weld metal is said to have poor weldability. Slight addition of reactive gases to the shielding gas, such as carbon dioxide, helps welding arc stability. Although carbon dioxide can break into oxygen and carbon due to high heat, it's not a problem when welding carbon steel and low alloy steel. But for high alloy steel, it can increase percentage of carbon that would reduce the corrosion resistance, and hence for high alloy steel, inertial shielding gas or mixture with only a slight addition of reactive gas CO2 is used. Physical properties. Physical properties of metal are melting temperature, thermal conductivity, electrical conductivity, coefficient of thermal expansion, and density. Melting temperature of metal is important for welding purpose because if the melting point is high, then more heat input is needed. This is achieved by increasing the amperage. And then obviously, if you have more heat, then that means difficult welding and more weld defects, plus thermal stresses are higher. Thermal conductivity. Materials with high thermal conductivity require higher heat input to weld than those with lower thermal conductivity because of quicker heat dissipation and the need to maintain the temperature during welding. A preheat may be used to lower the temperature difference, slowing down heat dissipation and avoid thermal stresses. A material that has substantial alloying elements would have a lower thermal conductivity, and lower heat input are required to raise the material to the desired temperature. The higher the thermal conductivity, the more difficult to weld because higher heat input is needed. Aluminum, for example, has higher thermal conductivity than steel and hence difficult to weld. It either doesn't melt, or you increase the temperature, it burns through. Electrical conductivity. Aluminum and copper have high electrical conductivity as compared to iron and steel. This is one of the reasons that copper and aluminum are used in electric wiring and cables. Also, because steel has lower conductivity or more electrical resistance, it needs less heat input because it gets some of the required heat due to resistance against electricity. The coefficient of thermal expansion describes how the size of an object changes with a change in temperature. The increase in length with increased temperature per degree is expressed as the coefficient of thermal expansion. If the metals expand or stretches more with increasing temperature, that is, it has high coefficient of thermal expansion, then it is more prone to warping and distortion problem during welding. When two dissimilar metals such as carbon steel and stainless steel with different coefficient of thermal expansion welded together, cracking can occur because of the difference in thermal expansion that leads to thermal fatigue. Density is weight per unit volume. Weld has less density than the base metal due to porosity and also being formed by casting, and hence looks brighter in the radiograph as more radioactive ray passes through it than the base metal. Denser shielding gas is more preferred because it can protect the weld over a longer period. Mechanical properties. They are tensile strength, yield strength, ductility, hardness, and toughness. Materials are selected by the welding engineer that should meet the design requirements in terms of strength, ductility, and toughness. Inspectors should understand the underlying principle of mechanical properties and the nature of tests conducted to verify the value of those properties. Tensile strength is the maximum stress that the metal can withstand per unit length before breaking. Yield strength is the maximum stress before the metal goes into plastic deformation, that is changing shape permanently. So as you can see here, there is a stress-strain curve. This is the horizontal one is a strain. This is the stress. So as you apply the stress, the material stretches, and you can see you got the graph here, a straight line. It comes to a point which is called the yield point, when on the graph the material, the stress applied is a bit reduced. There is a loop here, and this is because it went into yield strength. That means up to this point, yield strength, if you remove the load, the material goes back the same way up and down this graph the same way. So there is no metallurgical change on the material. But at this point where the stress goes to equal to yield strength, it goes into plastic deformation and it hardens. And then again, you see that here it's a curve, it's not a straight line, until the ultimate strength, and then it goes back to a point where the cross section is so thin that it breaks finally at this point, X point. So they call it strain hardening. There are two phases happening, and then the necking happens. Necking means the cross section would start thinning and thinning, becoming smaller. The Young's modulus is actually the tangent of this curve. So stress divided by strain, and normally this is a standard tensile test specimen where from the ends is gripped by the machine, and they stop pulling it apart until where here the necking occurs, a point. So this necking is actually this point here. This point here, I mean this area where the necking starts, where to a point where it totally breaks down, and that is the ultimate. The stress is the applied load divided by original cross-section area of a material. Strain is the amount that the material deforms per unit length in a tensile test. Toughness is the ability of the material to absorb energy and practically deform without fracturing. Plastically deform without fracturing. In quantitative terms, toughness is a stress-strain curve. You can see here there are three materials that have been toughness tested, the stress-strain. One, it has little strain, not much of deformation, but it's the strongest. But as you can see, this area under the stress-strain curve, or the energy observed, is the least. You can see the second material, it's both the strength is good and also stress. It took a lot of load while string until it breaks. So this got a large area of toughness compared to other two. Stress-strain curve, a larger area, so that's called the toughest. And there is a material which doesn't have much of a strength, but it has a lot of ductility. I mean, it stretches a lot, and then it breaks. Fracture toughness is usually measured by sharp impact test. So practically there is a swing here, they bring it to 90-degree or horizontal position and they just release it, and it comes here and hits the material, and there is a notch here, and as much as it goes up, it is shown here. So the difference between vertical line and this line is actually the Sharpie value, because the rest is observed by the material itself, the force of impact. So the tougher it is, you have less swing after it's hitting that the sample or coupon, Sharpie test coupon. Ductility is the material's ability to undergo deformation before rupture or breaking. Permanent deformation or plastic deformation resulting from plastic flow occurs when the elastic limit is exceeded. The bend test is used to evaluate the relative ductility and soundness of the weld joint or weld test specimen. So this is a bend test. There is a mandrel, it keeps pressing it, and then it's stuck between these two jaws until it breaks. And then you do a macro here to see that the weld is sound. There is no defect on the cross section, and then the amount of load applied and the distance it applied, it tells you how tough it was or how ductile it was. If it is brittle, it will break faster with a lesser distance, a lesser load, and if it is ductile, it will resist the load and over a longer period and distance. Hardness is the resistance to plastic deformation by indentation. So when we say hardness, it's different from toughness because it's on the surface. Hardness measurements can provide information about the metallurgical changes caused by welding. For example, you always have a higher hardness at the heat affected zone due to thermal differences between the base metal and the weld. So that's the most heat affected. So normally a very hard pointer or the shape of a circular shape or a diamond shape is forced onto that, and then this diameter and the diameter of the dent, or the length of the dent it creates, or the depth it creates, this shows plus the load applied. With this combination we can come back with a number and a value. For example, we got different hardness instruments like Rockwell, Vickers, and Brinell. Rockwell test is simple and rapid measurement hardness. The value of 55 and a C scale is expressed 55 HRC. H stands for hardness, R for the Rockwell, and then a letter indicating a scale employed. So Vickers hardness value is preceded by designation HV, also referred to as a micro hardness test method. It's mostly used for small parts and thin section. Preheating slows the cooling rate and reduces the risk of hydrogen-induced delay cracking. This may be necessary to avoid cracking of the weld metal or heat-affected zone. Need for preheat increases with steel thickness, weld strength, and carbon alloy content of the steel and the diffusible hydrogen of the weld metal. Preheat is commonly applied with fuel gas torches or electrical resistance heater. Purpose of preheat are reduce risk of hydrogen cracking, reduce the hardness of the weld and heat affected zone, reduce shrinkage stress during cooling, and improve the distribution of residual stress, evaporates the moisture from the fit up and weld area. Preheat should be applied and extended to at least 2 inches on either side of the weld to encompass the weld and potential heat affected zone area. The main purpose of post-weld heat treatment is to relax thermal stresses caused during welding, more pronounced for thick material, and reduce the hardness of heat affected zone, HAZ. Post-weld heat treatment can be localized, electrical resistance heating, or be placed in the furnace. Post-weld heat treatment procedure includes number of thermometers, maximum temperature difference between the furnace, heating and cooling rate and holding time, calibration of thermocouples. Hardening is the depth of hardness induced by quenching. It is different from hardness resistance to indentation. Hardness depends on the carbon content, while hardening depends on the alloying elements. A typical test of hardenability is called the Jomini bar. In this test, a round bar is heated to a predetermined elevated temperature until heated evenly across the cross-section. The specimen then subjected to rapid quenching by spraying water against the bottom end of the round bar. The hardness of the test specimen is measured as a function of distance away from the surface being quenched. Steel that obtain high hardness well away from quenched surfaces are considered to have high hardenability. Conversely, steel that do not harden well away from the quenched surface are considered to have low hardenability. Hardenability of the steel is an indirect indicator of weldability. As the hardness of base metal increases, so does the susceptibility to hydrogen-assisted cracking. And you can go to table 11, Brennan hardness limit for steels in refining services. It has some good information, like for base metal Brennan value, the hardness limit is 200. For chromium half mole is 225, and 1/4 chromium half mole is 225, and 2¼ chromium 1 mole is 241, and the 579 or 9 chromium mole is 241, and 12 chromium is 241, rest are 241. So as you can see, unfortunately, you need to remember this, the hardness limit. This is called a practical type of question. These two might be potential question, 225, 241, but as you can see, there are three numbers, 200, 225, and 241. So anything above, you just need to remember three numbers here. Material test reports. Material test reports are two types: heat analysis and product analysis. Heat analysis is issued by mill manufacturer for billet and ignot, also called mill certificate. The ignot and billet is worked over, casting, forging, forming by the manufacturer, who issues a heat analysis report and a statement of the chemical analysis of the end product. MTR normally has the following information: name of the manufacturer and date, heat number, batch number, compliance standard of the heat of the material, chemical composition, ultimate tensile strength, percentage of elongation, any possible heat treatment or Sharpie test values, any ND test such as lamination check. The inspector needs to verify whether the MTR meets the project specification or material requirement. The welding engineer may look at material certificate to determine its weldability. Carbon equivalent can be calculated from the chemical analysis. There's a formula for carbon equivalent. So weldability of metals means how easy a metal can be welded. In general, if the welding variables of the metal have a wide range, the metal has a good weldability. On the other hand, if the welding variables are narrow with restrictions, the metal has poor weldability. Metallurgy and weldability. Chemical composition of metal is a primary factor on weldability of metals. So this can be a potential exam question. The primary factor of weldability of metals, what is it? It is chemical composition. Carbon is added to carbon steel and alloy steel to improve strength. So carbon is for strength, but at the same time, carbon reduces the weldability of metal to a large extent, while other metals such as manganese, chromium, molybdenum, vanadium, silicon, nickel, and copper can reduce weldability of metals to a lesser extent. There is a formula called carbon equivalent by IW that we brought as below. You can use this formula. Higher carbon equivalent means poorer weldability. Typically, steels with a carbon equivalent less than 0.35 require no preheat. Steels with a carbon equivalent of 0.35 to 0.55 require preheat, and over 0.55 carbon equivalent require both preheating and a post-weld heat treatment. This can be a potential question. Weldability testing means how easy you can weld a joint and how wide the range of variables would be. Narrow range of variables and the need for preheat, post-valley treatment, restrictions on heat input, high hardness of metals, higher coefficient of thermal expansion, brittleness are all signs of poor weldability. The simplest weldability tests are those that evaluate the strength, tensile test, ductility, bend test and hardness test, and toughness, Sharpie impact test of the weld. Typical weld restraint test methods include daily high restraint test, slot test, rigid restraint cracking test, and circular weld restraint cracking test. The high test covers all weldability tests except lamellar tearing test. Weldability of high alloys. Chromium and nickel increase the corrosion resistance of alloys. Metals with chromium content of 9% and less are called low alloy, and over 9% chromium are called high alloys. Hot cracking in alloys is the formation of shrinkage crack during the solidification of weld metal. Hot cracking is known as hot shortness, hot fissuring, solidification cracking, and liquefaction cracking. This is due to poor flow of liquid weld metal. To prevent, use wider joint, lower welding speed, lower heat input, and shallow penetration, and a wider weld pool. Authentic stainless steel. Stainless steel up to 9% chromium are classed as low alloy, as we said, and above 9% are high alloys. Authentic stainless steel need the minimum ferrite number to resist hot cracking. Thermal expansion of stainless steel is 30% more than carbon steel, so the distortion is more for stainless than carbon steel. This means more tack welding needed for stainless steel to hold the weld joint in place during welding. During welding, the stainless steel, its house region is exposed to high temperature, around 800 degree to 1650 degree Fahrenheit, or 400 to 900 degree centigrade. The carbon may react with stainless steel chromium, forming chromium carbide, reducing the amount of effective chromium in stainless steel, therefore reducing its ability to resist corrosion. Use of low carbon stainless steel can prevent it. And nickel alloys. Alloys with nickel content of 35% or more, called nickel alloys, because penetration is a problem. And welding nickel alloys, wider weld joint is used. Also, the weld pool should be solidified as soon as possible to minimize the risk of lamellar tearing. Hence, preheat is not advised for nickel alloys welding because of the minimizing the lamellar tearing. Because preheating slows down the cooling rate by reducing the temperature difference between the weld pool and the base metal. And it's actually harmful because it prolongs the solidification process. So nickel alloys, 35% or more, called nickel alloys, and it's the only alloy that preheat is harmful actually. Thank you.